All right, this is going to be lecture 3, part 3, the third video in our little series on chemical equilibrium and chapter 14. All right, so just as a recap, we talked about what Kc was, okay? And remember we said in the first video that Kc is always equal to the product concentrations, okay, over the reactant concentrations, okay? And we said if Kc is a big number, it's mostly products. If it's a small number, it's mostly reactants. Okay. And so in this video, we're going to talk a little bit more about how to solve for Kc and then how to compare Kc to something we call Qc. Okay. And Qc is also the products over the reactants. Okay, so some of you might be thinking, okay, if it's the same thing, product over reactants, what's the difference? The difference is this: the concentration of the products and the reactants when you calculate Kc are at equilibrium. Okay, which means that the forward rate and the reverse rate have equal one another, and so the concentration of the product and reactants are not changing. Okay. Qc, you have products over reactants, but these concentrations are not at equilibrium. Okay? And by comparing Qc to Kc, you can actually predict which way the reaction will shift, whether it'll shift to the left towards the products, or whether the reaction is going to shift more towards the right towards the products, or shift more towards the left towards the reactants. Okay? All right, so before we get into that, though, the book goes into a little bit of how you might solve for Kc for an overall reaction given two elementary reactions. Okay, and just as a reminder from our previous chapter, okay, when you have two elementary reactions, oftentimes you have a reaction intermediate. In this case, we have two reaction intermediates. Okay. Reaction intermediate number 1 is the CH4. It appears before and after. It appears as a reactant and as a product. And we have the H2. There are 3 of them. 3 of them appear before the reaction. And so we can cross off the 4 and write a 1 here. Okay, meaning 3 of them are used up. Okay. So really, the overall reaction, if you bring everything down except for the reaction intermediates that you've crossed out, is CO plus 2H2S gives you CS2 plus H2O and H2. Okay? So let's say that you have this elementary reaction. You have the Kc for the first reaction and Kc for the second reaction. Okay? 3.92 for the first, 3.3 times 10 to the fourth for the second. You would like to know what is the Kc for the overall reaction. Okay? Well, they tell you if you multiply these two Kc's together, let's call it K1 and K2, okay? The products of the over reactants for the first reaction and products over reactants for the second reaction. Notice your CH4 concentrations cancel out and your H3 concentrations, 3 of them cancel out, okay? So what you are left with is your carbon sulfide, your water, and your H2 at the top, and your CO and H2S at the bottom. Notice, this is the products, or are the products, for your overall reaction. These guys here is these 3 here. Okay? And notice that your reactants are at the bottom in terms of your overall reaction. Okay? They're the same. Okay? So really, this is the Kc for the overall reaction, is it not? So if you multiply K1 and K2, which is basically Kc for your two elementary reactions, you're going to get K3 or Kc for your overall reaction. And in this case, if you do that, you multiply these two numbers together, okay, you're going to get 1.3 times 10 to the fifth. Okay? So really what all it's saying is, if you have, and this is just a lot of words, but really if you have, just to sum it up, if we have A plus B gives you C, and then you have C plus A gives you D, right? Your reaction intermediate is C, okay? Let's say that Kc for this reaction is 5, and the Kc for this reaction is 2, okay? Your overall reaction is going to be A and A, or 2A plus B gives you D, okay? And so the Kc for this end reaction is going to be 5 times 2, or Kc is going to be equal to 10 for the overall reaction. That's all it's saying, okay? All right. One more note, very important, in terms of reactions, there are oftentimes a homogeneous equilibrium in which the equilibrium involves reactants and products in a single phase, like all gas, for example, or all aqueous, okay? There's something called a heterogeneous equilibrium, and that's an equilibrium where the reactant and products are in more than one phase. So, for example, in this reaction here, notice you have iron is a solid, H2O is a gas, iron oxide is a solid, and H2 is a gas, okay? The general rule here is that you should omit. Omit means leave out, okay? You should leave out or cross out, okay, the concentration terms for solids and liquids, because the concentration of pure solids and liquids do not change, okay? The concentration is the mass over the volume. As the concentration of a solid reacts, the outer surface reacts, but the mass over the volume does not change, okay? So therefore, when it comes to solids, we just leave them out of the equation altogether. So normally you would say FeO3H2 on the top is the products, Fe and H2O on the bottom as the reactants. But because iron is a solid, we're going to cross that out, okay? And because iron oxide is a solid, we're going to cross that out as well. Remember, it's a solid, we're going to cross it out. It's a solid, we're going to cross it out. This simplifies it into H2 to the fourth, H2O to the fourth, okay? Now, the reason that we can cross it out, quote, quote, is that we're really multiplying it to the other side. So what we're doing is we're multiplying this by the concentration of Fe, and we're multiplying this side by the concentration of Fe3O4. And we're going to do the same on this side, okay? Okay. So when you do that, the Fe cancels out, the Fe3O cancels out, and that's why we can cross them out, okay? If you do this math, really it leaves you with this expression here, okay, where you have Fe to the third, okay, sorry, it's to the third, okay, divided by Fe3O4 times Kc is equal to H2 to the fourth, H2O to the fourth. Remember, Fe concentration is a constant, Fe3O4 concentration is a constant, Kc is a constant. So a constant divided by a constant times a constant is still a constant. We're just going to call this new constant Kc. And so therefore, we're just going to say Kc is equal to the H2 concentration over the H2O concentration, both of them to the fourth power. Okay? Ultimately, the takeaway from this is if it's a solid, leave it out of your Kc expression. Okay? If it is a solid, leave it out of your Kc expression. So then the book walks you through an example of how to use an equilibrium constant in different chemical scenarios. In this video, we're only going to cover 1 and 2, and then in the next video we will cover 3, because 3 is a lot of math, and so we're going to separate that out into another video. Okay. So really 1 says qualitatively interpreting the equilibrium constant by merely looking at the magnitude, i.e. how large or how small Kc is, you can tell whether a particular equilibrium favors products or reactants. And we already actually covered this, so this is really a review of that first point. Okay. 2, by predicting the direction of the reaction, you can consider a reaction mixture that is not at equilibrium. We're going to call that QC. Okay. And by substituting the concentrations of substances that exist in a reaction mixture into our expression for Kc, you can predict whether the reaction will proceed toward the product or reactants. Okay, and we're going to talk about how to calculate QC in just 1 second. Okay, so first and foremost, number 1, if you consider that Kc is equal to products divided by reactants, if the product concentration is large, the reaction lies towards the right, towards the product. So we're going to say reactants to products. Okay. So if the product concentration is large, and we're just going to put in pretend concentrations, 1 times 10 to the 8th. So that's 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So a lot of zeros there. And let's say you have 1 as your reactant concentration. Really, your Kc is going to be equal to this divided by this, right? So it's going to be equal to 1 times 10 to the 8th, which is much, much greater than 1, okay? Because your products are much, much greater than your reactants, i.e. if Kc is large, mostly products, okay? And on the other hand, if you have very little products, 1 times 10 to the minus 8, that's 0.00000000001. I've lost track of my zeros, but you know what I mean. So if that's the case, then your Kc is going to equal products divided by reactants, or 1.00 times 10 to the minus 8, okay? And therefore, because of that, you're saying there is much more reactants than there are products. Kc is a small number, okay? Really, we've already covered this in the first video. If Kc is large, it's mostly products. If Kc is small, it's mostly reactants. If I were you, and if you haven't done so already, I would pause the video and write this down in my periodic table. Kc is large, greater than 1. Then we would say that...
I've been told I have a big personality.
What? I don't know why my phone is talking to me. I apologize. But if Kc is greater than 1, or much, much greater than 1, it's mostly products. That was weird. My phone was talking to me. Kc is much, much less than 1. It's mostly reactants. Okay. I would write this down in my periodic table, or on my periodic table. We should add one more. If Kc is equal to 1, it is at equilibrium. Sorry, not at equilibrium. I take that back. It is products equals reactants. Reactants. Okay? Wow, it's really messy handwriting. Okay? So I would write this down on my periodic table if you have not done so already. Okay? So that you will have it with you when you're taking exams and quizzes and homeworks and stuff. All right, so your book gives you this nice little table, and it says you've got this reaction, A plus B, and it gives you C and D is large. If Kc is large, the equilibrium is mostly products. If Kc is small, the equilibrium is mostly reactants. And when Kc is around 1, the equilibrium mixture contains appreciable amounts of both reactants and products. Basically what we just said. All right. The second part of this video is talking about how we can predict the direction of the reaction. And really the question is it going to shift to the left, or is it going to shift to the right? Okay, that's the question. So again, you're considering this reaction, A plus B gives you C and D. Remember, Qc is not at equilibrium. Okay, and so you have products over reactants. Okay, and again, these are not at equilibrium. Okay, you're going to plug them in, and you're going to compare this number to Kc. Okay, and if Qc is greater than Kc, the reaction will go to the left, towards the reactants. If Qc is less than Kc, it'll go to the right, towards the products. And if Qc equals Kc, obviously the reaction is at equilibrium because Qc equals Kc. Okay, and the book gives you a little bit of a picture here of Kc here. Sorry, if Qc is less than Kc, then it's going to the right. If Qc is greater than Kc, it's going to go to the left. Okay. Again, I would also write this down on my periodic table, this little green box here, because it will help you to remember which way it'll shift left or right in predicting it. So if you haven't done so already, again, I would pause the video and write this down. So let's look at an example of exactly this little application. You have a 50-liter reaction vessel. It contains a mole of nitrogen, 3 moles of hydrogen, and 5 moles of NH3, not at equilibrium. Okay. Will more ammonia, NH3, be formed, or will it dissociate when the mixture goes to equilibrium? So they're asking you basically, is it going to shift to the left, to the right, towards the more ammonia, okay? Or is it going to shift to the, is it going to shift to the right and disassociate? I apologize, let me repeat that again. Is it going to shift towards the right and form more ammonia? Or is it going to shift towards the left? The ammonia is going to disassociate and form more N2 and H2. Okay, so let's plug in what we know. We know that we have 1 mole in a 50-liter flask, so the molarity or the moles per liter is 1 divided by 50, which gives me 0.02. 3 moles of H2 divided by 50 gives me 0.06. And 5 moles of NH3 divided by 50 gives me 0.01. Okay, we're going to plug this in, and again, it's products over reactants. So I have my NH3 here. Okay, it is squared because of the 2 in front of the NH3. And I have my N2 and my H2. And again, the H2 is to the third because of the coefficient in front of the H2. This comes out to 23.1 if you do the math. And it tells us that Kc is 0.5, or 5 times 10 to the minus 1. Okay, so really, if you're looking at Qc is 23 and Kc is 0.5, Qc is greater than Kc. Okay, so if Qc is greater than Kc, let's look back at our table here. The reaction will go to the left, meaning it'll shift to the left. Okay, so that means that it's going to shift towards the reactants this way. Okay, which means the NH3 is going to dissociate and form more N2 and 3 H2s. Okay, let's look at another example. Okay, it says here you've got a 10-liter vessel, and it contains 0.0015 moles of CO2, 0.1 mole of CO. Okay, and it says if a small amount of carbon is added to this vessel and the temperature is raised to 100 degrees Celsius, will more CO form? Okay, and they tell you that the Kc value is 1.17 to compare it with. Okay, so using all that information, let's calculate what the concentration of CO2 is. Initially, it is going to be 0.0015 moles divided by a 10-liter flask. That's nice because it just moved the decimal point. Again, it is 0.0015. Okay. And then you have the concentration of CO, which is 0.1 moles over 10 liters. And again, you just move the decimal point, so it becomes 0.01 capital M. Okay. With these two values in hand, let's set up QC. And remember, QC is equal to, the products, which is CO. And because I have a 2 in front, I'm going to square this, divided by CO2 and C. Okay, now notice C is a solid. So what did we say before is that because it's a solid, we don't include it in our expressions. We're going to cross that out. So really it's equal to CO2 CO squared divided by CO2. Okay. So let's plug in our numbers. Our CO is 0.010. Squared divided by our CO2, which is 0.00015. So this comes out to 0.67. Okay, don't forget the square there. Okay, so let's compare QC to KC. QC and KC. QC is 0.67. KC is 1.17. So KC in this case is greater than QC. So it is the second situation. It's going to shift to the right. Okay. So will more CO form? If it's shifting to the right, that's in this direction. Okay. More CO will form. Okay. Shifting to the right, pushing it to the right, creating more CO. Okay. All right, so this ends this video. Again, there are really a couple of takeaway points. One is how to calculate QC and compare it to KC. And then based on that, you should be able to predict, will it shift to the left or to the right? Very, very important is that you calculate the molarity first, okay, before you plug it into the QC. That is the most common mistake I've seen, is you don't calculate the molarity first. That throws off your QC value, and when you compare it to KC, it's incorrect. So make sure under no to first solve for the molarity. We did it here, okay, and we did it here. Okay, so solve for the molarity, plug it into QC, okay? The other takeaway point is really, based on KC values, you can determine or tell if it's mostly product or mostly reactants at equilibrium, okay? And last but not least, we have two major things where if you have a solid, you don't include it in your KC expression. And also, if you have two elementary reactions and an overall reaction, the way to calculate KC for the overall reaction is to multiply the KCs for your two elementary reactions. All right, so I'm going to stop the video here. This is the end of Lecture 3, Part 3. I would again do your homework based on this material before continuing further and watching the next video.